Our speaker tonight is Tom Crowley, a KT4XN, who is probably one of the preeminent speakers on the subject of radio astronomy related to amateur radio. Tom has been chairman of the board of the Atlanta Astronomy Club. He's past president of the Society of Amateur Radio Astronomy, SARA, which I would urge many of you to join, if not all of you tonight, if you have an interest in this topic. He's chairman of the Jupiter Radio Project for SARA. He's Southeast coordinator for the SETI League and is currently research associate at Georgia Tech in the Physics and Astronomy Department. He was first licensed in 1957 as Kilo November 2 TMT, and he currently holds the extra class license of KT4XN. In the past, he's also held a first class radio license. At Georgia Tech, Tom is responsible for the implementation and maintenance of a remote optical telescope at Space Force Maui Remote Experimental Station. The telescope utilizes both a CCD and video camera that are used for Georgia Tech students and outreach for Georgia students. Tom enjoys visual viewing with an 18 or 24-inch Dobsonian telescope, astrophotography with an LX200, and radio astronomy looking at cold hydrogen in our galaxy with a radio telescope. Now that's good DX, Tom. So he is also part of the NASA Radio Jove project, looking at Jovian radio storms and sudden ionospheric disturbances from our sun. Career-wise, Tom started with Boeing Aerospace on the Minuteman ICBM project and then spent 29 years with IBM. He took an opportunity for early retirement. The last 10 years were spent in international electronic communications, with a highlight being vice president of a metro media company responsible for designing and building a European fiber backbone network. Tom, let me turn it over without further ado. Tom Crowley, KT4XN. Over to you, Tom.
Well, I'm delighted to be here. I wish I was there in person. I grew up and graduated from Lowell High School. So the topic tonight is going to be radio astronomy. We'll touch a little bit upon, as we get started, looking at the electromagnetic spectrum. One of the things that many of us forget or don't realize is that a photon is a photon and its frequency is dependent on how energetic it is. We consider the radio photons to be fairly lazy, X-ray and above, gamma rays fairly active, so they're much, much higher frequencies. The Society of Amateur Radio Astronomers, you can find that at radio-astronomy.org. Suggest you go out there, take a look. We also run a grant program for students. So if you know a student that wants to get involved in a project with radio astronomy, we will fund that project for him. And on the SARA website, there's instructions on how to do that. So let's get started. We'll do an introduction to radio astronomy. We'll talk a little bit about the electromagnetic spectrum. We'll look at some of the professional radio telescopes. We'll discuss some of the discoveries made. Then we'll finally get to amateur radio astronomy, what's being done. So radio, it's part of the electromagnetic spectrum along with light. We tend to think of light as something visual and radio as something using electronics. As we look at the spectrum, the higher we go in the spectrum, we get into gamma rays, nuclear transitions. You come down into X-rays, which are not quite as active. Ultraviolet, you get to the very small visible spectrum, often called RGBIV, which tells you from the low frequency to the high frequency what the colors are. Infrared, where the James Webb telescope will be mostly operating. Into microwave, we know that is 2 meters, 70 centimeters and above. And then finally, radio. This is just another view of the spectrum, kind of looking at wavelengths at the top. I don't know how easy that is for you to see, but the less energetic, the longer the wavelength, the more energetic, the shorter the wavelength. And this kind of just shows various sizes of things in comparison. Looking at the electromagnetic spectrum, and in astronomy, it's interesting. We have gotten away to some extent from optical telescopes on the ground to putting them up in space. Up in space, they can see a lot more. They don't have the atmosphere to go through. So looking gamma rays, X-rays, and the satellites that look at those, they can see the hot interstellar gases. You can see black holes, or you see the accretion disk around the black hole, supernovas, gas jets. You come down into the ultraviolet solar flares and young stars, which are very hot, into the visible, where we can see galaxies, stars, the solar spectrum. Infrared, we start getting into the interstellar dust clouds, of which there's a lot, and we can see each other. Interestingly enough, if you have direct TV at KU band, you can detect humans with that. Also, you can see trees. All of us are radiated about 300 degrees Kelvin, a little bit less than that. And then we get into the cosmic microwave background. We'll chat about that later. And gas jets and other things you can see in the radio spectrum. Looking at the visual spectrum on the right, on the top, that's what our galaxy looks like. If we look at it at 400 megahertz in the bottom, you see that we actually see a lot more of our galaxy looking at 400 megahertz than we can see in the optical frequencies. In the optical frequencies, if you look at that bright bar toward the center, you'll see some dark lanes, and that's actually dust that's blocking the visual view, much in the way that when we look up at the heavens and we have clouds we can't see. Taking a look at why do we use different frequencies for astronomy, looking at 400 megahertz, 0.4 gigahertz, you can see the coming across, you see quite a bit of information. You can see through the dust lanes. The very bright center is Sagittarius, the center of our galaxy. Atomic hydrogen is 1.421 gigahertz, and our galaxy is filled with what's called neutral hydrogen. We'll talk a little bit about that later. Looking at radio at 2.7 gigahertz, you can see that the images begin to change. Molecular hydrogen, which is higher, begins to change. Infrared changes again. Mid-infrared, again, a lot different. Near infrared, and these are the three frequencies that the James Webb is concentrating on. Looking at the optical, you can see a bright spot toward the center of the galaxy, but you see all these dark lanes. The dark lanes are hydrogen gas and dust and dirt. You have to remember that we're all made from stardust. Looking at X-rays, we still see the dark lanes, and you see some differences in the brighter areas. Gamma rays, again, it's different. And then there's a finder chart on the bottom that kind of lets you know where things are in relationship to the galaxy. So why radio? And what causes the radio emissions that the astronomers are looking at? So we'll kind of discuss that. If you go out to the National Radio Astronomy Observatory.edu, NRAO.edu, there's lots of good information on radio astronomy. I highly recommend that. So what can we see from Earth? We can see from about 15 megahertz on up to maybe 130 gigahertz. There's a few other holes that we can see, but the radio spectrum has the most. We get the color spectrum, a little bit of infrared, not much, and then the sky is opaque. So in order to be able to see these other frequencies, we need to have satellites away from the Earth's atmosphere. The only two things, again, that are available are optical and radio. And in radio with at least 100 times more observable wavelengths than optical. So at the different wavelengths, we can detect different things. Our natural paradigms is we think of radio as sound. And when giving this to an astronomy club or to lay people, you have to convince them that radio is not sound. Radio is frequency in the electromagnetic spectrum. If you saw the movie Contact, this is where Jodie Foster is there listening for ET with her little laptop with a very large array in the background. So how did we come about radio astronomy? Who discovered it? Carl Jansky built the antenna on the right there. It's kind of similar to a beverage. And he was charged by ATT to find a way to communicate using radio waves with Europe. So that was his challenge. What happened was that we didn't get undersea cable for voice until about 1957. And so any voice traffic had to go by radio. So he was working 10 to 20 meters, found somewhere around 15 meters to typically be the best, going down to 20 meters. Not a surprise for those of us that do HF and hunt DX. So he recorded and he found thunderstorms, distant thunderstorms, and there was a faint hiss of an unknown origin. He could not understand what that was. He spent a year investigating and then realized that what he was looking at rose and fell every day. And it varied by 93 hours, 54 minutes, which is the time it takes the Earth to rotate once, 56 minutes. So he figured out the radiation was coming from the Milky Way. At first he thought it was the sun, but wasn't the right direction. And then he realized it was coming from the center of the Milky Way in the galaxy Sagittarius. Well, what he was seeing, unbeknown to him and to most others until the 1950s, was that he was the original discoverer of the black hole in the center of our galaxy. What he was seeing was the electrons in the accretion disk. As it went around the black hole, the electrons became free and like naughty little children, did what they wanted at any frequency. So you can look and see that at almost all radio frequencies above 15 megahertz. Below 15 megahertz, the sky is opaque. We just really can't get out and see it. The D layer just really prevents that. So the discovery was published in 1933. ATT really didn't want this to get out because now suddenly the phone company was communicating with ET. But the New York Times published it. Jansky wanted to do a follow-up, but Bell Labs said, no, that was it. You found what we wanted you to find. You can move on to another project. The next guy was Grote Reber. He was a electrical engineer building radio receivers. In his backyard in Wheaton, Illinois, he built this 40-foot dish. If anybody is interested, I have plans for that and can send it to you. He learned about Jansky's discovery. He applied to ATT for a job, wasn't accepted. So in 1937, he built this in his mother's backyard. His mother, by the way, was a fifth grade teacher of Edwin Hubble, of the Hubble telescope, and Hubble had made some great discoveries. Reber spent long hours every night. If you think about in the 30s, probably most of us weren't there then, but automobiles really didn't have radios in them, so there was no reason to quiet down the ignition systems, and they used just copper wire for the ignition system as opposed to the carbon wire that reduces the emissions from that. he had made 2 attempts, and he finally succeeded creating a receiver at 160 megahertz to detect the radio emissions. And as you can see on his charts, you see all the lines going up. Well, that's, for the most part, automotive ignitions, thunderstorms, that kind of thing. So moving on from 38 to 43, he made a survey of the radio waves and published his results in engineering and astronomy journals. And if you look, he had laid out the signal strength of the various radio emissions he was detecting, mostly from our galaxy. There was very little interest in radio astronomy. It wasn't until World War II that the British radar was being blocked by the Germans, and the Germans would attack during the Battle of Britain, and they couldn't understand how the Germans were blocking their radar. So a guy by the name of Hill, I believe, Hill Hall, was given a top secret project to make that discovery, what's going on and how are the Germans blocking it. What he realized was the Germans were attacking in the afternoon with the sun to their back. So the radar was picking up the sun and blocking the aircraft. That was top secret for many, many years. The Orion complex is reasonably new. Somewhere between 30 and 100 million years ago, a cloud of hydrogen came through our galaxy, and it's called Gould's Belt. All of the new star growth has pretty much come from that. The Orion complex that you'll start seeing in December, January, with Orion the Great Hunter, is one of the very active areas of this new star birth. And looking at that in the radio frequencies, the green objects that you're seeing are radio objects. These are objects that are emitting in the radio frequencies. Looking at the telescopes that are currently, there's a number of telescopes currently in use. The National Radio Astronomy Observatory in Green Bank, which National Science Foundation a number of years ago decided not to fund them. So now they're being funded by individuals and colleges. But this site, Green Bank, West Virginia, sits in a valley, and it's well protected. When you took your ham radio license, you learned about the radio quiet zone. Well, this is the reason for the radio quiet zone. The telescopes that they have, this aerial picture does a good view. If you look on the lower right, there's an 85-foot dish. If you follow that road up, you'll see a second 85-foot dish and a third one. The third one was used, called the Tattle Telescope, and that was used by Frank Drake looking for ET in the 1960s. The great big telescope, the Green Bank Telescope, is looking in front of us. It's as tall as the Statue of Liberty. By comparison, there is the receiver room looks like and is the size of a 2-car garage. All of the receivers are up in that. The dish is offset, much like a direct TV dish, and it's controlled in alt and azimuth, so altitude and azimuth. It weighs 17 million pounds. It was designed to come in at 16 million, and each wheel carries a little bit over 1 million pounds of 16 wheels. Just behind that dish, you'll see a telescope that's being worked on. That's a 140-foot equatorial telescope that had recently been used by the Russians, and when the Russians were using it, everything on that site was locked down. So that's kind of a quick view of the Green Bank telescopes. We're currently using 4. There's a 40-foot educational, which looks at the hydrogen line, 1420 megahertz. 20-meter educational that Sarah has access to remotely, so that we can actually run that telescope from our homes. the 140-foot equatorial, the 100-meter Green Bank telescope, which goes from 100 kilohertz up to 70 gigahertz. And there's a 45-foot solar scope that's also used that looks at the sun. What's been discovered with radio astronomy? Quasars, quasi-stellar things. They didn't know what they were. Zenith, I believe, named a TV after that, quasar. And what they are very early galaxies. Now, talk about DX. My best DX is about 2.3 billion light years. Looking at one of these quasars, and I've seen that optically, and I've seen it at 1420 megahertz using that 40-foot telescope. Cosmic microwave background, we'll chat a little bit about that. Pulsars were originally thought to be little green men. Neutral hydrogen, which is cold hydrogen, we'll talk about that. Black holes, of course, temperature of Venus, and Jovian radiation. So we'll kind of touch on those topics moving on. Temperature of Venus, serendipitous. One of the things about astronomy and radio astronomy, a lot of the discoveries are serendipitous. By that, we stumble into it. And if we have enough knowledge and money, we can then make a great discovery. The Naval Radio Observatory, which is across the mountain from Green Bank, looked at Venus, and they found it was radiating more energy than they expected. They were able to determine the surface temperature at 600 degrees Fahrenheit, about 320 degrees Celsius. One of the things with radio telescopes is the scientists consider them to be giant telescopes. So instead of looking at gain in decibels, they look at gain in temperatures, degrees Kelvin. Kelvin starts at absolute zero and comes up. Looking at the centigrade scale, it's equivalent to the centigrade scale, and we're almost 300 degrees Kelvin on a nice summer's day, around 80 degrees. Cosmic microwave background. This one's fun. It was first detected in 1941, but nobody knew or understood what it was. Over in Princeton, just down the road from you folks, Dickey and Peoples had predicted that there was a cosmic microwave background. Penzias and Wilson, working for ATT, were testing a satellite receiver. They had 3 degrees Kelvin that they couldn't explain in 1965. Penzias calls his buddy Bernie Burke up at MIT. He's asking Burke how his sailboat racing is going, and Burke says to him, "What are you guys working on at ATT?" And he says, "Well, we've developed a satellite receiver, and we're having trouble. We found 3 degrees Kelvin that we can't explain. It's not noise in the receiver. We sent some grad students up to clean out the horn antenna that they're using that you can see there, thinking it was bird poop that was causing it. That wasn't it." So what happens is Burke says to Penzias, he says, "You know, the guys over at Princeton, Dickey and Peoples, are doing a paper, and they're trying to get funding to find what you guys just found. Why don't you give them a call and see what's going on?" So they did, and Peoples said to Dickey after the call, "We've been scooped." So Penzias and Wilson got the Nobel Prize for it. Dickey and Peoples got a cup of coffee. So much for Nobel Prizes. If you take a look on the lower right, that is one of the CMB images, and you'll see some dark areas in there, and you'll see some brighter areas, the yellowish, reddish areas. That's actually where galaxies are, and that's where galaxies were beginning to form about 300,000 years after the Big Bang. So it's quite a find. There's been quite a bit of work since 1965 that found the temperatures in the cosmic microwave background to be extremely constant, within 1,000. So amazing discovery, and it kind of gave proof to perhaps the Big Bang did happen. Moving on, looking at the Very Large Array, which is on the plains of St. Augustine in New Mexico. There's 27 25-meter antennas. They can put it in 4 different configurations. The farthest configuration gives them, if it were an optical telescope, it would be 36 kilometers in size. The mirror would be 36 kilometers. And it has a sensitivity of 130-meter antenna. So pretty powerful. And its ability to resolve images is phenomenal. They move it into 4 different configurations depending on what they're looking at. And that's done at different times a year. The Green Bank telescope, it's about 100 meters. As we said, it's 0.1 to 160 gigahertz, 3 meters to 2.6 millimeters. It actually gets down to into the 300 megacycles range, and it's heavy. They shut it down for maintenance every summer, and people go up, inspect the welds, and check it. Green Bank had a 300-foot telescope that collapsed in the, late 70s. And it was caused by bad weld, and it came down. So the Senator Byrd from West Virginia worked hard to get Congress to fund the new telescope. Again, that's another view of the Green Bank, and you can look at the mountains in the background and the valley. It is bothered by a few things. There's a airport in Roanoke, Virginia, and that radar sweeps by here and will occasionally affect these telescopes depending on weather and some other factors that will have an effect. And also the issue of cell phones, and the worst offender is Wi-Fi. They have a friend of mine who is known as a noise Nazi. He has got a truck, he's got a semi-trailer that's filled with electronic equipment, and he goes out and hunts things down. Some of the funnier things that they found was that in the winter, there was a heating blanket in a doghouse to keep the dog warm in winter. West Virginia can get pretty chilly. And that was causing RFI affecting the radio telescopes. So they went and they replaced the electric blanket. The farmer across the street had a tractor that was gasoline, and they went and tuned that up for him because the spark plugs were causing RFI. So they'll go out of their way to resolve the RFI issues around the area. One of the newest is the Atacama Large Millimeter Array. And this is in Chile, and it's pretty high up. This is interesting. It's looking at north, and you're seeing the star tracks going around the North Star. There's 66 antennas. They're about 14 meters each. They're at 5,000 meters, 15,000 feet, a little bit higher. To get people to work up there, they had promised the workers that there would be a naked woman behind every tree. Well, at 15,000 feet, you don't have a lot of trees. It works from 31 to 1,000 gigahertz. The cost was $1.3 billion, and we funded almost half of it with $500 million funding. The telescopes are brought in for service and moved with this tractor that you see there. And with most things today, everything is done remotely. So let's talk about imaging, radio versus optical. I'm sure all of you have a digital camera or perhaps a cell phone that can take pictures. And when you take a picture with a cell phone, you've got a CCD chip and millions of dots, millions of pixels on those CCD cameras. The readout is interesting, but you get a tremendous amount of data off of our cell phones. And it's photodiodes collecting the light, and they're set so that you can get red, green, and blue. and combining that with a little bit of math, you end up getting color images. We typically don't see pixels. Maybe as a kid, you took the comic section of the newspaper, looked at it under a microscope, and you saw all these dots that really weren't visible when you looked at the comic strip. So if we take a look at the deer here and we look at his ear, we can see the individual square pixels in the ear. And that's basically how the optical cameras work. And some of the images, you can see solar flares, the Eagle Nebula, a galaxy M51, Halley's Comet, the globular clusters. So they're pretty popular in astronomy, whether professional or amateur. And amateurs now are taking images that the professionals couldn't do 20, 25 years ago. So that whole optical science is just pretty amazing, and how it's grown, as all of that science has. So how do we image in radio? I think we all remember the CRTs in the old TVs. And if you remembered how that worked, it did a scan, and it scanned one pixel at a time and effectively lit that pixel or didn't light it. And in black and white, it varied with intensity, so you'd get shades of gray. And it would do a scan, there was a flyback, and it would scan again. It always scanned left to right. With a radio telescope, you do a scan left to right, and then you do a scan back. So the radio telescope is really a one pixel camera, and you do that to collect the data of the object that you're trying to image in the radio frequencies. Takes hours, days, or years. Doing a full sky for an amateur can take several years, and lots of the amateurs have done it. Radio imaging resolution, it's interesting because using the very long base array, which is worldwide, you can get you can get down to a 1 degree angle, and you can split that. So you can get the milliarc second in size. Milliarc second, what's that referring to? If you think of a circle as 360 degrees, each one of those degrees has 60 minutes. Each one of those minutes has 60 seconds. So now we're getting into sub-millisecond, arc second. So it gets pretty small. So that means that we can see a hair at 10 miles with a radio telescope. And an optical telescope can get to 5 milliarc seconds with the Keck telescopes on Hawaii. So radio telescopes are actually a lot more powerful than the opticals. The other thing that you can do is you can take an image and then 6 months later take another image and combine those, and now you've got a mirror that is effectively the radius of the Earth's circle around the sun. So among friends, 186 million miles across. So can't quite do that with the optical telescopes yet. Radio imaging, this is an amateur taking a look at Sagittarius, and you see the energy increasing as you hit the center of the galaxy and the black hole in the center of the galaxy, which is pretty active. You can then combine that over a number of days. You get an image like this, and then running it through Excel or a program such as that, you can produce an image something like this. So even amateurs have the ability to do imaging with a 3 meter or 10-foot dish. The professionals, you can look at neutral gas in the Milky Way, a quasar, that little white dot in the center, is shooting electrons, photons out, and they begin to slow down. So you get these bursts of energy that are out there. Looking at the galactic center, you can see a lot of activity in there, looking at the temperatures, various temperatures. looking at the galaxy M81, which is a nearby galaxy in our local group. You can pick up atomic hydrogen, which you can see in the red. There's another radio galaxy where it's shooting the photons out. And then Saturn, you're picking up the temperature of Saturn with the rings and looking at Saturn itself. So lots of different things. And again, the images are quite a bit different from what we can see on the optical spectrum. Neutral hydrogen. Neutral hydrogen was proposed in the 50s and discovered in the 60s. It's 1420.41 megahertz. And what it is, if you get an electron between 5 and 20 degrees Kelvin at ground state, that's the lowest state of the electron. If it stays there for 10 million years, then a quantum transition occurs called a hyperfine transition. And that electron flips over. When that electron does a flip, it releases one photon at 1420.41 megahertz. There's enough hydrogen out there that it's fairly easy to detect in a 1 meter dish. With this, you can detect the rotation of the galaxy. So I did a project and did a paper that looked at the rotation of the galaxy. And you use Doppler shift to determine the speed of the neutral hydrogen, referred to as HI or H1. You then, using a little bit of math, you take it and make it heliocentric so that you're looking at it as if we were taking the image from the sun. Looking at the voltage, peak frequency is minus 65 kilohertz off of 1420.41. So we come up with a velocity of 300 kilometers per second. Among friends, that's a little bit, maybe 185, 190 miles per second is how fast that cloud of hydrogen is moving. This is basically how you do it. The cloud was at a right ascension of 19 hours, 16 minutes with a declination of minus 22, 60 kilohertz frequency shift, peak at 1340. So this one is approaching 14.29 kilometers per second. So that's still getting pretty quick. So almost 32,000 miles per hour. The thing in astronomy, when you look at the speeds that things move, it's pretty amazing. If you look at the rotation of the Earth or the rotation as we go around the sun, those speeds are phenomenal, and you wonder why we don't get thrown off, or at least I do. Pulsars. Pulsars were discovered by Jocelyn Bell in England, and she found some things that were occurring, and she labeled them LGM, little green men, thinking perhaps they were ET. But what they ended up to be is that when a star goes supernova, type 1A supernova, it can do one of two things. It can go in, it can become a black hole, or it can become a neutron star. That neutron star spins up very, very rapidly, and the Vela pulsar spins at 0.089 seconds, one revolution. The electromagnetic field from that comes out really the strongest around 300 megahertz. It's detected as low as 30 megahertz, 39 megahertz. University of Florida detected it at 39 megahertz, and there was a doctoral dissertation done on that. So we see a number of pulsars. We don't see them all because that pulse of energy has to be facing the Earth. So if it's facing anything but the Earth, we are not going to see that pulsar. There's a project going on in West Virginia for the high school kids to take the data and to see if they can discover pulsars. And they've been pretty successful at that. Another view of the pulsar is you have that neutron star in the center, you've got the spin axis, and then the magnetic axis, and if it's pointing to Earth, we're able to see it. Other things that we have is that in the center of most of these galaxies is a black hole. The accretion disk of the matter dust stars sweeping around that will release their electrons, and they're referred to as free electrons. So looking at Virgo A, 53 million light years away, that we see this output, which is coming off the center of its galaxy. So there's amazing things that are detected. Black holes, predicted 1783. We think there's a supermassive black hole in almost every galaxy. And again, they're created from a supernova, type 1 supernova collapse. They begin to feed on themselves and just increase in size. Radio jets, M87 is another galaxy. Its jet comes out 5 light years. And we're finding more and more of those in the different galaxies that we look at. Imaging the black hole itself is extremely small when you look at it in arc seconds. In the past year or so, they did optical and radio observations and came up with an image similar to this. When we look at it and image it with a radio telescope alone, we kind of get the image of a duck, amazingly enough. So what can the amateur do? And what do you need if you're deciding on a project? Electronic know-how. So most of us hams have some electronics. I'm a EE by trade. What do you want to do? What do you want to look at? How expensive? It used to be 10, 15 years ago, $3,000 could build you a 1420 telescope. Now, $300 can do it. The Society of Amateur Radio Astronomers, on their website, we have folks that can help someone getting started. We do a lot of work with kids with the grant program, and the kids will send them a radio telescope. We ask that they send us a report on what they're doing. Currently, I'm working with a student here in Georgia on a 1420 radio telescope. She's a senior, and she'll be looking at the rotation of the galaxy. So I'm helping her with that. This kind of gives the radio projects you can do at various frequencies. There's something called the Itty Bitty Telescope, which is really about 10 gigahertz, and it's really an educational telescope for kids. You can see the sun. Some, if they're really super strong, you can see the moon. You can see people, you can see trees, anything 300 degrees Kelvin and above, which is pretty much everything on a typical summer day. Hydrogen is one of the big things. OH, which is looking at hydroxyl, which is really water that gets hit with ultraviolet, and after 72 hours, one of the H's goes away. So you pick up hydroxyl at about 1667 megahertz. There's actually 4 frequencies that they go from. HF, looking Jupiter and solar are the popular ones, Radio Jove. And if you Google Radio Jove, you can see how to build one of these. If you have a 15-meter antenna, the cost to you is about $130. HRO sells an SDR 1A. I think they're around $130, and that's all you need to do that. I've got one operating right now on my desktop, and it's showing the neighborhood RFI at the moment. Whistler radio, this is getting down into the very low frequencies, 10 to 50 kilohertz. This is also a NASA project. It detects lightning, aurora, solar flares, and it's interesting. Most of it is showing activity on Earth. And here's an image of what happens looking at the different frequencies. Solar flares, I have to announce, this is an image my wife took with a solar telescope. The CME's cycle 25 was supposed to be a dud. What we're seeing with cycle 25, and if you're a DXer and you follow this, you're finding that it's more active than we had expected it to be. Not sure what's going to happen in the future, but will it be more active than cycle 24 or not? We were supposed to be going down into a cooling cycle of the sun. The sun's a variable star. We've been in something called modern maximum for over 70 years, where the sun's output has been a bit higher, contributing to global warming. So the CMEs and the flares, of course, affect DE and F layer. I was on a Wednesday on something called CW Ops, a 1-hour CW contest. Suddenly the band went away as a solar flare hit. This is beginning to tell you or show you the different radio flares that can be detected. There is another project where we look at transmissions to submarines coming from Cutler, Maine. And if there's a CME, it affects the F layer and it affects that transmission. So that becomes a neat project. Here's that flare coming in, and they're in it M1.6 and M2.3, and you see the effect of the two flares over on the right on the chart. Again, solar radio, and this is looking at the very low frequencies, really 20 to 40 kilohertz. Other projects, media detection, Jupiter radio, which is the Radio Jove project. Gamma ray bursts, some guys are trying to get that. You really need a fairly large dish to do it. Some of the guys are getting pulsars in 4 and 6 meter dishes, and interferometry, which is taking multiple radio telescopes and putting them together. Media detection, you're looking at radio and TV stations that are farther away, typically 500 miles away. And when a meteor comes in, that signal bounces off that meteor. You also have hams on 2 meters, 70 centimeters doing the same thing, especially with JT8 and those kinds of programs. So it bounces off the ionized trail of the meteor coming in. It's kind of a fun project. The Canadians did a major project with this with the high school students. Looking at that and charting it, here's the spectrum that you can see if you're doing something a little bit more advanced. Radio Jupiter, there's 2 kinds of storms. Typically, you look between 15 and 29 megahertz. Below 15, the signals are attenuated because the D layer just gets in the way and just doesn't let you see those. There's 2 kinds of bursts, the L burst, long burst, which is something referred to as a non-Io A storm. Io is the nearest moon to Jupiter. And this is the magnetic field sweeping and hitting the Earth, and there's an electrical storm going on that we detect. And it sounds pretty much like the crashing of waves on a seashore, kind of hitting a pebbly beach. If you're using 15 meters, and if Jupiter's in the sky, you may hear this as a shh kind of sound. It's really shh kind of noise. The other type is a short burst, which is the interaction. It's called an Io base storm, A, B, and C, D storms, and that sounds more like sounds more like a machine gun going off. So those are the things that are detected. Right now, Jupiter is up in the afternoon and early evening, and we're detecting a lot of these storms. Interferometry, you take 2 telescopes, you put it together, and what happens is that they add and subtract to each other. So you get an increase in signal, decrease in signal. And this is looking at a chart of the fringes that you'll get. So that's it. As technology continues to improve, the costs come way down and amateurs can get more and more involved. So that's what I've got. I suggest going to the radio-astronomy.org website, the SARA website. There's a lot more information. I'm going to stop sharing the screen. Okay,
There we go. Tom, thank you so much. This was a great presentation.